Here we go. I'll try to zoom that in. Thanks, Rachel. So here we are. Today is Friday. Happy Friday. That means there's a quiz starting today. Remember, those are due on Sundays, right around midnight, 1 minute before midnight. I think we should maybe change it till 2 minutes till midnight. Anybody? No, it's Iron Maiden. Is it 3 minutes? I don't know. There's an Iron Maiden song. I'm pretty sure it's called 2 minutes till midnight. Okay. That's a deep cut for all of you. Also, today is our last day for open hours visits. We've sent out several reminders. So I think at this point, you got to make it happen. It's worth 4% of your grade. That's right. 4 whole percentage points of your grade. That's more than a quiz. So go get them. Come and see me, Mike, or Rachel. At this point, there are no scheduled open hours, so you will have to find time to meet with us via appointment. So get on that email real quick. Okay, so that was part one of our agenda. Our agenda is pretty slim today. We've got a little bit of lecture here, do a little practice together, and then in Chem 101 is groups. And then for lecture 2, we'll go back to, I don't know, today's kind of some mind-blowing stuff, if I say so myself. I think this stuff is really cool, but also a bit challenging. So I would love questions. Feel free to interrupt me at any time. You can just start talking. You can do the little raise hand function. I usually see that, or you can type it in the chat. I love the chat too. Feel free to use the chat, especially because we have Rachel and Mike here who can interact with you in the chat as well. So that's, just want to encourage you all to get involved as much as you can in class. I don't know about you. I think a lot of us are feeling a little trapped is maybe the wrong word, but maybe closer than we'd like it to be. Maybe missing that social connection a little bit. Anyone who came to my office hours, you got your ears talked off. So, let's connect. Turn on your video if you feel up to it. See each other's faces. You get to be seen that way. That's good too. But hit up the chat. Use those emojis. Let's connect. Okay, enough of that. Let's get into the material.
Oh, Graham, can I say one thing real quick, please?
Absolutely, Mike.
Okay, sorry. Tuesday's lab, since we are not meeting Monday because of Martin Luther King Day, for Tuesday's lab, we are going to be doing the synthesis of copper oxide. Okay, so if you would please write an introduction prior to lab. Read through the material, be a little bit prepared, and write an introduction before you come into lab. Thank you.
Did you know, fun fact, when I go into the lab myself to do my research, original research, did you know I write an introduction to all my experiments too? I literally do. I have a lab notebook and it says like, okay, trying the prep from Wang et al. We're going to do this thing that they tried and we'll see if it works in our hands. And right, I do. It's usually short, doesn't have to be a lot, but it does help me remember what I thought 6 days ago or 6 months ago, God forbid, 6 years ago, right? All of those things have to happen. So that's there. I'll bring in my lab notebook sometime. I'll hold it up and you can all see what my chicken scratch looks like. All right, let's dive in. Here comes some slides, some pictures. I wanted to start by zooming back a little, taking a step back and going back. I lit some stuff on fire. I thought it was quite pretty. We got some good screenshots. Rachel grabbed some good screenshots. But what's the point of that? Well, my point here is we've been talking about matter, and then we decided that matter is really importantly these teeny tiny itsy bitsy little things, right? And those are called atoms, and we can't see them because they're so small. So we need tools to interact with these individual atoms or molecules on our macroscopic scale, right? Well, how do we do that? Well, one way we've seen, I got Amadeo up here, Amadeo Avogadro, his number is kind of our link to correlating mass in grams to individual atomic masses, right? That's our translational number that lets us weigh things out on a balance, for instance, and understand what we're handling in terms of quantities of atoms. So that's super, super helpful for us. And just as the mole allows us to translate atoms and molecules into something we can touch, feel, manipulate, right? Light gives us that kind of power as well. I can see things. It's one of my 5 senses. And we can even use those five senses in scientific ways and ascribe numbers and values to them. And that gives us a handle on the energy of the atoms or molecules that we're looking at. Okay, so this is kind of, that stepping back. What are we doing as chemists? We are trying to understand the molecular scale world from our perspective as these, relatively enormous colossus creatures, right? We are all colossi when it comes to looking at atoms. So that I left you with another mystery at the end of last lecture, which was when we shine a light, that's a white light. So something like an incandescent bulb, maybe a flame from a fire, a red hot glowing piece of iron, something like that. We get this white light spectrum, right? It broadens out and it seems a pretty rainbow. We've all seen this, right? Sunlight shines through your window and it catches it just right, and you see the little prismatic effect, and it got a little rainbow on your wall or something. Everyone seen that before? Some of you have seen that, right? Yeah. Ryan, thanks. Ashlyn, cool. Emma, awesome. Well, when we do this with light sources that are special, light sources like a helium lamp gives us a spectrum with just some lines, right? So if that were to catch the window just right, we wouldn't see that pretty rainbow on the wall. We'd see some weird lines. If that worked out. That's quite an experiment to try to make happen. Okay, so that's cool. Same thing with a barium lamp. We get weird lines. Same thing with an oxygen lamp. Weird lines plus a little bit in the background maybe. And same thing with a neon lamp. We've all seen neon lamps probably. The open sign in the bagel store down the street, right? That's usually made out of neon. It's literally neon gas inside of a tube with electrical plates on either side to excite the atoms and make them give off this light. So why does the light come in these little lines rather than a spectrum like we see with other things? That's a big mystery for all the scientists back in the day. Okay, so what causes that? Let's look a little deeper though. Let's do what the scientists did and think about these lines in specific. Okay, so the first thing we'll do as scientists is we'll use the property of light that we have. This ability for us to take this microscopic molecular size information that we get, the line spectra, and let's turn it into usable numbers, okay? So I'd look at my lines and I can assign them to our scale. And in this case, we can assign them to our scale of nanometers. We know the wavelength of light. And this is kind of a modern interpretation. Way back then, they would literally project their spectrum onto the wall and they would measure it with a ruler and by how far away from the prism you were. And then they got these fancy things called spectroscopes. It's all very, very interesting. But we have modern technology that kind of lets us skip a few of those steps, right? And so we can look at the hydrogen spectrum. That's what the H here means. And we see that the hydrogen spectrum has 4 visible lines, 4 lines in the visible spectrum. And in fact, we can go so far as to give those specific wavelength values. Okay, so we'll see this one here is around 410. This one's about 435. If I'm kind of, this one's what, 487, something like that, and 650 and change. Okay, so this guy, he's a school teacher teaching kiddos younger than all of us, but he's really interested in all the world, and he does tons of reading. His name's Johannes Balmer. Went ahead and figured out a pattern. He was able to mathematically find a pattern, an equation that actually took those 4 values of those wavelengths and related them to each other, all 4 of them to one another, right? He was able to mathematically describe this relationship between the wavelengths of those lights. This is amazing stuff. And that relationship ended up, you can write it in this form here. This is lambda, that's our wavelength, equals 364.56, some constant, just a number that he found, times m squared over m squared minus n squared. Turns out n is just 2 in this case, and then m can be 3, 4, 5, or 6. Okay, so we have 4 values of m, 1 value of n. That gives us 4 possible outcomes here, 4 lines. Feel free to go ahead and plug these into your calculator and see if you get wavelength lines that correspond to any of these 4. Should we do that? Should we do that really quick? Just try to plug one of those in. Here, I'll try it. 364.56. I mean, this is exciting TV right here. Should we do 5? Let's do 5 squared All right, and then we'll divide that by the quantity of 25 minus 4. 434. All right, so when I put in 5 for my value of M, and when I put in 2 for N, because that's what these are, I get 434. That was one of the numbers I read to you before. I guess I said 435. That's this pinkish line right here. Some of you might call it purple. Okay, so that's the value for 5. I'm going to just make an educated guess here that this would be, if I was M equals 3, it would be this reddish line. M equals 4, blue, 5, purple, and 6 would be the even brighter purple. Mike, thanks. Mike did M equals 3. He got 656. Boy, oh boy, that's right on the money for the red one. That's pretty cool. Okay, I'm going to come back to this bottom equation. This bottom equation you can see, and it always D subscripts my age. I don't know why. Has kind of a similar format to this one. Here we flipped it around 1 over wavelength, and now we've kind of simplified. We have one value for N and another value for N, N1 and N2, right? And this new constant called the RH, the Rydberg constant. Let's come back to that one, okay? Which is to say that these are the 4 lines we can see with our eyes on a spectroscope, but there's more lines for hydrogen that you can't see. All right. Interestingly, I just kind of wanted to point this out. This works the other way too. If you take a white light, incandescent bulb, for instance, shine it through a sample of some gas, and then put that white light through a slit and then through a prism onto a screen, you'll see all the white light except the lines that you would see from the emission spectra. Okay, so in the previous one, we were exciting the atoms themselves, and that excitation gave rise to giving off that light. And what we see in these pictures here for hydrogen, helium, and neon is we can actually absorb the light at those same frequencies. And we'll double check. There's one for 434. That's pretty darn close. This one would be Mike's number, 634. Okay, so we do see absorption in the same patterns that we see emission, whether we're exciting or we're absorbing light. Does that make sense to everybody? Yeah, I think it's cool and pretty amazing. Okay, we need an explanation for this. How the hell is this happening? This doesn't make any sense. But what we see is these discrete lines. Okay, and this is going to take us now back to our ideas of waves and quantization, right? So this guy, Niels Bohr, he's in my top 10 favorite scientists. He's not my #1 favorite scientist. That's Marie Curie. And if you don't agree with me that Marie Curie is the best scientist of all time, let's fight. I'll go to the mats for Marie Curie. Absolutely. All right. So Niels Bohr, and this is in conversation with a ton of people. All right. Brilliant minds from all over the world are struggling with this problem, trying to figure out why these lines have these shapes and everything. He comes up with this wild idea, and this was really received as a wild idea at the time. He says, okay, let's think about electrons as these particles, but these particles have a distance from the nucleus, right? And we know the nucleus at this time, he knows the nucleus is positively charged and the electrons are negatively charged. And so he knows that there's kind of an energy from that, right? We would think of that as, plus and minus charges attract each other. So there's an attraction energy. This electron then, if it's a particle, has to have a certain energy so that it doesn't crash into the nucleus. But what he says is, let's say they have to have a certain distance from the nucleus and they have to maintain that distance. They can't get any closer or further away. And if they do that, we'll call those an orbit, and that will correspond to a certain energy. We've kind of seen this, many of you have probably seen this picture before, or a version of this picture, right? Here's our nucleus in black, and then n equals 1 is this small gray circle here, right? And plus ZE, that would be our nuclear charge. E is the value of a charge. Z would be our number of protons. We've seen those numbers before. So we've got ZE here. That's our nucleus. We have our n equals 1. That's an orbit, pretty close to the nucleus. We could say that there's an electron in that orbit. Then there's another orbit further away. That would be another place an electron could be. Then there's another orbit further away. That could be another place an electron could be. And what Bohr said was the electron can jump between these different orbits. Okay, so it's only allowed to be in one of these 3 orbits, or one of the many orbits, right? There's actually more than 3. This is just illustration, only has 3. Okay, and electrons are only allowed to be in those specific places. And when we see absorption or emission, what we're seeing is an electron jumping from one orbit to another. Okay, so whether we're seeing emission would be the giving off of a photon, right? That's a change in energy. What we're saying is that electron is changing energy when it goes from one orbit to another, which makes sense. You gotta have a different energy if you're closer to the nucleus. And when that energy changes, it's either changing by the absorption or the emission of a photon. Okay, I'm gonna pause for a second and see if anyone has questions about this, and then I'm gonna ask you some questions. Okay, no questions from you. So here are questions for you. I'm saying here that we can absorb or emit a photon. So let's say an electron absorbs a photon. What's going to happen to the energy of that electron?
I'm guessing it will increase.
Okay, Gordon says it's going to change, and he's going to be even bolder and say it's going to increase. And I would agree with you, Gordon, because if you absorb a photon, right, that photon has energy. We saw that last lecture. We saw that E equals h nu. Photons have frequency, they have energy, right? And that photon gets swallowed up by our electron somehow through magic, I guess, right? Sufficiently advanced science. It's not magic. We have an explanation, but we're not going to get into it in this class. But that photon with its energy gets absorbed by our electron. Suddenly, boom, our electron has more energy. Okay. And that extra energy is going to make it go farther away from the nucleus, because as I said before, the closer you are to the nucleus, the stronger that attraction is. And so if you absorb a photon, you're going to jump out to an outer level. Okay, so that would be the process associated with these pictures, absorption of light. How about the emission of light, the one that we saw in our cool rainbow flames demo? If an electron is giving out energy in the form of a photon, which way is it going? Is it getting further or closer to the nucleus?
Further from the nucleus.
Well, you said when it absorbs a photon, it's going to get further from the nucleus, right? We're jumping up in energy. Think about it like this. Okay, you have two things that attract each other. Let's use magnets just as an example. It's kind of a useful, this is an analogy, right? This isn't the effect, but it's an analogous effect. If I have two magnets, the closer they get, the more they attract, right? Let's now put one in the middle. I got a magnet in the middle, and then I put another magnet on a string and I swing it around. Okay, is that magnet, if I swing it faster, give it more energy, is it going to get further or closer to the magnet in the center? Right, the faster, the more energy that outer magnet has, the further out it's going to be able to go, because it's going to be able to resist or counteract that attractive force. Okay, so if we have, and let's go back to our example. If we're emitting a photon, if our electron is giving off energy, it has less energy then to counteract that force of attraction from the nucleus. And so when it gives off that photon, it's going to jump into a more inner, more orbital. I hope that makes some sense. Okay, this follows a very simple equation. We're all familiar with the change in energy of our electron in this case is equal to h nu. This looks almost identical to a previous equation, right? E equals h nu. That is the energy of a photon is equal to Planck's constant times its frequency. Well, here, the change in energy of our electron is equal to Planck's constant times the frequency of the emitted or absorbed photon. And we have to think about which direction the sign of E should go, if the energy is increasing or decreasing. All right, let's take another look. So here's the same picture on a new graphic. We have our nucleus in red in the center, and we got n equals 1, 2, 3, 4, and 5. So the further out we get, the higher the number for n that we give it. And when I look at these, we can actually assign these transitions based on Balmer's equation. This is fascinating. So school teacher in the 1800s figured out an equation that maps onto Bohr's theory. Okay, so if we look at electron here from orbit 3 jumping to orbit 2, we go ahead and plug that into an equation, and that will apply. That's the one Mike calculated for us. In this case, it's 657 nanometers. Right, 434, that's the one I calculated. That's a bigger jump. That's from n equals 5 down to n equals 2. That's the one I calculated. So that's really interesting. I mean, this is amazing, right? We have an empirical formula from Balmer, and now we have a theory behind that formula. This is a wonderful example of kind of the scientific method evolving over time. First thing we see is an observation. What's going on with these lines? The second thing we do is we try to model that observation. We look at it by saying, mathematically, what does this look like? Okay, that's Balmer. He says, I made an equation, check it out, it works. I don't know why. And then lots and lots of thoughts. 100 years later, Bohr comes in and says, how about this? Maybe this works. Okay, so it does work. And let's go now back to that second equation on that slide. Again, another depiction of the same phenomenon. Okay, now we're not showing the nucleus at all. Now we're saying the orbits are just these horizontal lines. So orbit 1, which we showed as a circle around a ball before, is now just this horizontal line down here. Then we have 2, 3, 4, there's 5 and 6, right? So lots of lines. And we see they get closer together as we go farther out. Okay, and you see here also that this is labeled as the principal quantum number. We'll come back to quantum numbers. That's not for today, but this will be useful to come back and see this then. And what we see is these green lines, the green double-headed arrows here. Those are going to be our Balmer lines, as they're known now. Those are the 4 visible lines in the hydrogen spectrum. Again, the one I calculated was the 5 to 2 jump, where m equals 5 and n equals 2. Mike calculated 3 to 2, and then 4 to 2 and 6 to 2 are also in the visible spectrum. Those are not the only lines visible in the hydrogen spectrum. If you expand your spectrometer a little bit and get into values that are outside of our visual range as humans, we actually see lines in the ultraviolet. That's these pink lines here. There's 5 of those. And infrared, which is below red, so that's outside of our vision at the low energy side of the spectrum. We see these shorter double-headed arrows. Those are infrared. Okay, so we can actually map those out too, and we see all of these different transitions, and we see each of these lines corresponds to a transition between 2 different levels going around the nucleus. So another scientist comes through. His name is Rydberg, and he maps all of these transitions onto an equation that's very similar to the equation that Balmer proposed. Okay, we've got a couple fundamental constants in here. The Planck's constant and the speed of light are involved. And then we have this thing called the Rydberg constant, that's RH. So all of these are here. They're all constants, they don't ever change. The only thing here that changes is the values for n final and n initial. So this is called the Rydberg equation. And this tells us what we should expect the change in energy of that electron to be if it jumps from one thing to the other thing, one level to another level. And the H here is telling us that this is specific to hydrogen. So the Rydberg equation only applies to hydrogen atoms. I know there's a lot on this slide. Yeah, go ahead, Gordon.
I have a question. I'm a bit confused by this figure to the left. Is it like the closer you are to 0, is that like more energy or like less energy? And like what is the scale on like the right?
Great question. All right, so we can see the scale on the left answers your first question. Energy increases to the left, and that is specifically the energy of the electron. The electron's kinetic energy increases on the left. Okay, and then for the principal quantum number on the right, we'll come back to that. That's for a little down the road. Okay, but for now, let's just call that the orbit number, right? So we just number them sequentially from the center out. So we have the nucleus, then we have orbit 1, orbit 2, orbit 3, orbit 4. Those are the quantum levels that are allowed for our hydrogen to exist in.
And what about like going like vertically, like up and down?
Yep. So our electron has the least amount of kinetic energy at the lowest level, at level 1, and it has more energy as it goes further out away from the nucleus. That kinetic energy lets it kind of fight against the attractive force to the nucleus when we do that. It's a way to think about it. That also then helps us figure out that when we go from level 5 down to level 2, for instance, right, when our electron jumps down a level or several levels, that should emit a photon. It's going to give off energy. It's losing energy in the form of that photon. Okay, vice versa. If we want to bump up to a higher level, we're going to absorb a photon because we need to add energy to the electron to get it further away from that nucleus. And we'll see that in our delta E number, right? If our final, let's play this out in the equation form, right? We can use this equation to kind of help us keep track. Delta E is the change in energy of our electron. If our final number is higher than our initial number, this will be 1 over 25 minus 1 over 4 for the example I did. Well, 1 over 25 is a smaller number than 1 over 4. So this will all inside the parentheses, this will be a negative number. That negative number will cancel with the negative sign out here at the front. So we will be increasing the energy of our electron. That makes total sense because we're going from 2 to 5. That's up on our energy scale. Okay. Conversely, if it was 2 and 5, our final state was 2, our initial state was 5, we would see 1/4 minus 1/25. That's a positive number. Overall, then this term on the right is a negative term. So we would be losing energy in our electron. When we go from a higher level to a lower level, we lose energy. That's a negative sign. Okay, if we can also use this value, that's H times C times RH, gives you that constant number. Sorry, I got my Zoom window that blocks my upcoming what's coming next. Okay, so we can call a few little terms for you. We have the ground state, that's our lowest energy state. Okay, we have excited states. Many of those are up here. Those are just terms for you to kind of remember as we go. And now I have some practice problems for you. We'll do these together, okay? So do the following transitions represent absorption of energy or emission of energy? N equals 3 to N equals 1. All right, so to do this, I'm going to try some tech stuff. I'm going out on a limb here. We're trying something new. All right, do we have a new share that's happening? Look at that. I got this fancy iPad from the library, and now I can write right on it. So here's the same question. Do the following transitions represent absorption of energy or emission of energy? Everyone sees that? Hey, cool, that's fun. So N equals 3 to N equals 1. We could draw our picture. If the picture helps you remember, go ahead and draw it. This would be 3, 2, 1. So we're going, our electron is going from here down to there. Okay, would this be absorption or emission? Maybe you don't remember. Maybe that picture doesn't help you. Another way to do it. Oh, I'm sorry. Who was that? Lakin. Lakin says emission. How did you know, Lakin?
Because it's losing energy, so the energy has to go somewhere.
Okay, so the electron has less energy the closer it is to the nucleus, so that has to be emission. Maybe the picture is not helpful. Maybe you get confused. You can always rely on that Rydberg equation. We have some constant with a negative sign in front of it times 1 over N final squared minus 1 over N initial squared equals delta E. Okay, so if we do that, final is 1. So we have 1 over 1 minus 1 over 9 because our initial is 3. I'm plugging those values in for my n's. 1 minus 1/9 is a positive number. Our constant is a negative number. So our overall delta E must be negative as well. If we're losing energy, it must be going away. We must be emitting the energy. Okay, so two ways to solve this problem. Why don't we go ahead and work on the second one together? And then really quick, let me, oh, can I make a really fast poll? Uh-oh, I don't have polls ready. Should have had this one ready. How fast can I make a poll? Faster than you can solve the problem? Doubtful.
Polls are not fast.
No, it's like the least useful thing in Zoom.
And I have your Kathy Kodat generic poll ready.
Yep. Also, button clicking doesn't seem to work. All right, this one's called Untitled Question. All right, is it emission or absorption? Go ahead and choose it.
Is this for number one for the first question?
Sorry, this is for n equals 2 to n equals 4. We're doing this one now. Should I start it over? I don't know. Can you change your answer on the poll? It's
None
in
of you
an,
submitted it.
what's that, Rachel?
None of you already submitted it.
I'm just gonna leave it. If you had the wrong one because you did the wrong problem, you know, I'm not gonna look at who put which answer, so it's all right. All right, so the majority has it. I'm gonna stop the polling here. I got 39 answers. The results are in. It is probably absorption, at least if the process of me imparting information to you or you absorbing information. Yeah, there we go. I'm emitting information and you're absorbing it. It was absorption. That is true because we have a, we need to be heading up. Thanks, Emma. All right, so let's go back to a different screen. Can I find it? All right, not too bad. So let's talk just a little bit about the Bohr model. Why is it good? Why is it bad? Because this is not our final model. I'm just gonna come right out and say that. In 1922, this was Nobel Prize worthy stuff. This was incredible. This is brand new idea. I mean, we're kind of used to this, right? Like all the generic atom pictures are essentially the Bohr model, right? Sometimes they just twist the orbits and make it look cool, right? But if you see a cartoon of an atom, it looks like the Bohr model because that's a nice simple thing for us to decide. As it turns out, it's not our best model, but it was the best at the time. And the reason it was the best at the time is because it was a model that included the facts that electrons have discrete energies and that energy is absorbed or radiated when electrons are moved between discrete levels. These were huge, important discoveries, and a theory that explained those discoveries was massive. All right, but what are the limitations? All right, the first limitation, it only works for hydrogen. This doesn't make any sense beyond hydrogen. Other stuff is way too complicated. And just to remind you of that, here are some other spectra: helium, barium, oxygen, and neon. Helium's not as bad, right? It's got 6 lines instead of 4. I bet you could try to find a relationship there. Describe the relationship in the barium spectrum, or worse, neon. Like, look at neon. Look at how many lines are in neon. I don't know how you could possibly fit a Balmer equation to those. So thank goodness for humans, hydrogen was simple. This is a theme going all the way through your P-Chem classes if you go that far. All right, so only works for hydrogen. That's kind of a bummer, but it's still a great discovery. Electrons are not merely particles though, right? We've been talking about wave-like properties and including, so we've said that electrons are also quantized. There's something wave-like about electrons, and this theory doesn't really think of that, right? We've been thinking about a ball going around a stick or something capturing, getting hit by a photon. Those are all particle-like things. Okay, so that's a little bit about the Bohr model. Let's take a few minutes to stretch our brains. I'm going to open up a attendance on Chem 101 and also a activity. That's the word I'm looking for. Chem 101 is very slow. So let me first open attendance. Just push the start button. There it is. Okay, I think that should work. Today's code 0847. All right, once we're in there, we'll open up our breakout rooms. Looks like Rachel's got those set up already. Thank you, Rachel. Okay, you may need some of the slides, so I will go ahead and post these slides to Canvas already. All right, anyone having Chem 101 issues? All right, should be ready, should be available. There's 2 problems there for now. I'm going to add a 3rd problem while you're there. I had it, but it didn't save. Feel free to enter your breakout rooms whenever you are ready and work on those problems. I'll also post the slides to Canvas so you have the equations, the Rydberg and the Balmer equations. So those are heading to Canvas right now. Okay, the second one was a little, took a little bit of thinking, right? So I asked one of the breakout groups this question: what are the possible values of n?
Can it go up to anything?
It can,
Like-
Andrew. Yeah, it's
Okay.
it's actually any, well, not anything, right?
Well, is it just whole number values?
Any integer, that's right, any positive integer up to infinity. But it can't be anything in between, right? It has to be a whole number. Yep, exactly. All right. Were there other questions that came up?
Yeah, what does N represent?
So n is essentially, Gordon, that's a much bigger question than you even realize, right? So n represents a lot of things. It's called our principal quantum number, and there are some great equations that we'll get to in your lifetime, I'm sure. But for now, I'm just gonna keep it simple, and I'm gonna say n is a counting number that tells us which of those orbits, which level we're on. So if I'll share again here, go back to our discussion of the orb model, right? So n is essentially which of these orbits we're on. So none of my pictures have had an infinite number of orbits because I can't draw that many, but you can imagine them, right? So imagine that there are an infinite number of circles gradually getting farther and farther from the nucleus. N is just how far out are you? Which one of those levels are you on? That's what we're going to call it for now. There's more to it than that, though. All right, everyone ready to move on? Keep cruising here, I hope. Okay, so we're back to our last little limitation of the model, right? Electrons are not just particles. They have wave-like properties too. But this is actually not just a limitation. I think it's also a clue as to why things might be quantized. Okay, so let's think about this now. The wave nature of matter. All right, so if electrons have wave-like properties, we know electrons have mass. We have measured the mass of the electron. I think you've seen that in the lecture. Louis de Broglie, this guy who just looks like I would hang with this guy, right? He looks like fun. He suggests that if light has matter properties, then matter should have wave properties. This is a bonkers idea at the time. Let's try it. He tries it. He says, I got the relationship. I know a relationship between mass and wavelength. And for those of you who remember E equals mc squared, that may play into here a little bit too. Okay, but what we see here is he gets this equation. This is called the de Broglie equation. Lambda, our wavelength of something, equals Planck's constant, there it is again, over the mass of the thing in kilograms times its velocity. And those of you who've done a little physics might remember that mass times velocity is your momentum. So momentum is a key thing here. You could rewrite this as lambda equals h over p, where P is equal to mv. That's your momentum term. Okay, well, we got to try this. We're going to go straight to some practice problems. We're going to do these together. Let's see if this works. All right, so electrons. Aiden, what's up?
Can you go back one more time? I'm just trying to see the equation.
Absolutely. I'll leave it here for a second. These slides are up now on Canvas as well. Day 6 lecture
Okay.
notes is called.
And what's the second one below it?
This one here,
Yeah.
is that cut off on your screens?
Yes.
Oh, shoot. Lambda equals H over P.
Okay, thank you.
Is that cut off for anyone else? Give me a thumbs up if it's cut off for you too.
Looks fine on my side.
Okay, so a few of you have a Zoom issue. There is a way to change that in your Zoom. If you, I don't remember the button though. Aiden, I can't do that. Oh yeah, I'm gonna lower your hand now. There we go. Okay. All right. So let's try practice. Everyone got these equations written down? Okay. I hope so. Also, this one down here. Let's just really peek at this real quick. This is important. One of the things we haven't talked a ton about are the units for energy. And so the units for energy in SI is joules. But the joule is a compound unit. It comes out of other units that are more fundamental. So we know the kilogram, that's a unit of mass. We know the meter, a unit of length, and we know the second, that's a unit of time. Turns out 1 joule, 1 unit of energy, is 1 kilogram times meter squared over second squared. A kilogram meter squared per second squared. So that's going to be useful when we use this equation, because we're going to have lots of units we have to interconvert. So here's the problem. Let's try it. Calculate the velocity of a neutron whose de Broglie wavelength is 500 picometers. All right, I should be sharing again. All right, we see it? Okay, calculate the velocity of a neutron whose de Broglie wavelength is 500 picometers. Uh-oh, iPad's running out of battery. We can do it, iPad. All right, everybody, close your eyes for a second. I gotta twist it around. Oh, it doesn't even show that. That's cool. All right, here we go. So what's our equation? Our equation is lambda equals H over M times V. And here, this is important. That's V, not nu. And the two symbols are awfully close to each other, especially the italic V. So you gotta make sure you're keeping that one straight. You might even write vel if you're worried about it. All right, so lambda equals H over mv. But the question asks, what is the velocity of a neutron whose de Broglie wavelength is something? What I'm going to do is I'm going to rearrange this before I even get to solving anything, because I think it's easier to move around just a single letter than a whole number with units. So I'm going to change that around. I'm going to multiply both sides by velocity and divide both sides by lambda. And that way I get velocity equals H over mass times lambda. Zoom in a little bit. Good. Do we have H? Do we know what H is? Anyone got it?
Isn't that Planck's constant?
It is indeed. Planck's constant is on the previous slide, but I'll also write it here. 6.63 times 10 to the minus 34 joules per second. Okay, joules per second is also kilogram meter squared per second squared with another second on there. So actually 3 seconds now, just to remember. Okay, we also have M written right up here. And our wavelength, lambda, is 500 picometers. Sorry, it's cut off on the screen. So we could just plug all that in. We've got equals 6.63 times 10 to the minus 34. And because I'm solving for a speed, I think I need to have seconds. I don't have joules anywhere else, right? So if I use the joules per second from my Planck's constant, that's not going to be super helpful. So I'm going to write this whole thing out. Kilograms times meter squared per second squared times seconds. Okay, I can go ahead and divide that now by my mass. 1.67. Oops. I just flipped my pencil upside down and tried to do that. That didn't work. 1.675 times 10 to the minus 24 grams. Okay, we're going to need to do some work here because we have kilograms up here. We need to have this in kilograms. I can do a little dimensional analysis right down here. I have 1,000 grams.
Will that neutron mass be constant for every time we use this equation?
Every time you use this equation for a neutron, yes.
Okay.
1,000 grams per kilogram. That gets our units squared away there. And our length, de Broglie wavelength, is 500 picometers. Okay, so that's our mass term there. Here's our wavelength term, 500 picometers times, we need to convert those to meters. How many picometers in a meter? If you don't remember, I did post a chart to Canvas. It's in the top part of it. Oh, who is that? Sorry.
It's Bella, 10 to the negative 12.
10 to the negative 12. Okay, so we've got to be really careful here. A picometer is smaller than a meter. So we want to make sure that this makes sense. I'm going to put 1 meter on the top, and I'm going to say 10 to the 12th picometers on the bottom. And I need to just double check that. I have to do this myself every time. We're going to double check that to make sure that there's a lot of picometers and 1 meter. That makes sense to me because I know picometers should be small. Okay, so that's going to all cancel out. So here we go, 6.63 EE minus 34. And somebody in the chat said the units on Planck's constant are joules per second, right? Who said that? That was Mike. Oh, Mike, it's joules times seconds. Oh,
joules
my bad.
times seconds, right?
That's
so you're going to have one
better.
of the seconds cancel.
Thank you, Mike. Okay. Everyone's, I goofed that up. That's absolutely right. So this second's going to go away and this squared is going to go away because 2 of those are going to cancel out. That's going to work a lot better. Thank you, Mike. All right. And let me fix it right here too. There. Okay, cool. So just to double check, our grams are canceling. Our picometers are canceling. Our kilograms then are going to cancel. And one of our meters is going to cancel. We're going to be left with the unit of meters per second. Thank goodness Mike helped me out there, because otherwise we would have been left with meters per seconds cubed or something. That would have been not right. Meters per second sounds like a velocity to me, so that's good. Could punch all that into our calculator. If you get it, type it in the chat. All right, I get something. I got it wrong, I'm pretty sure. 7.916 with my significant digit over the 1. I've got my exponent wrong. Minus 34 divided by minus 24 leaves me with minus 10. Mike's got it. 791 meters per second. So 7.91 times 10 to the 2. Thanks, Mike. Thanks, Fiona. That's pretty fast. Aiden, what's up?
I got 0.7916.
All
I
right.
don't know how I got that. I just plugged that into the calculator and that's what I got.
All right. It probably, I'm guessing you missed the dividing by 1,000 grams because you're off by 3 orders of magnitude.
Divide by 1,000?
Well, divide by dividing by 1,000. So divide by 1 over 1,000, multiply by 1,000.
And how come? Or why do we?
Yeah, because we have at the bottom, we have to convert from grams to kilograms. And when we do that, we have a 1 over 1,000 term right here. And so since that's on the bottom,
Oh, okay, sorry.
that's all right. 2,800 kilometers an hour. Mike converted that for us, or 1,780 miles per hour. That is over the speed limit. Yep. Okay, so I'm going to leave the second practice problem for you to try on your own. It's a different arrangement of the same equation. Calculate the de Broglie wavelength of a 145 gram baseball. I think you have to give yourself a velocity there. So maybe it's thrown at 100 miles an hour. It's a good fastball in the major leagues. I'll also I will post that problem to Canvas later today. I'm going to finish up. I got a short video to show us after we finish our discussion here on de Broglie wavelength. Okay. Okay, so de Broglie's wave condition. Electrons are in a standing wave around the nucleus. Why is it standing? What does that mean? It means that the ends are fixed. It's like a guitar string, right? You have to fix the ends. So it must kind of be a complete wavelength from one end to the other, or a complete half wavelength actually. Okay, so this is what it would look like if it was a 1D wave. This is a 1D standing wave. Okay, it has 1, 2, 3, 4, 5 nodes, 2 full wavelengths. It's going to look like this. What does that look like in 2 dimensions? Here's a circle. That's a standing wave. Okay, with the little animation. That's kind of neat. So if it were the Bohr model with a spherical orbit, this might be our standing wave. That's pretty cool. But they have to fit perfectly around the orbit or we have destructive interference. So this illustration is kind of a 2-dimensional representation of a 3-dimensional phenomenon where we have our radius and our wave goes around, it's bent around itself, but it must connect at the end, right? So right here, there's 1 wavelength. So this is fully 1, 2, 3, 4, 5, 6 full wavelengths around. If we have a little more than that, and they don't meet up at a node or a peak, what we see is they will do this, and then we have to keep drawing our wave all the way around, and we get nothing. Destructive interference will occur, and our wave gets completely wiped out. This is really interesting. This means that we only have certain answers or certain arrangements of these waves around our 3-dimensional object for our electron to exist in. Okay, so this one on the left is good. That one is bad. We can skip this. This isn't super important information. Okay, the take home here is that we have restrictions on which wavelengths can describe our electron's motion. That sounds like quantization to me. Okay, so since the electrons in an atom must be standing waves around the nucleus, they can only have certain values and energies. Electrons must be quantized. What does 3D standing waves look like? I don't have a picture of that just yet, but I do have this cool video that brings a little music into things. So I'm going to have to stop this share and we'll watch the video from a different share here. Here we go. All right, I hope this doesn't blast your ears out. I'll start it low. Give me a thumbs up when it's starting to sound okay.
The first experiment for the cymatics music video is called a Chladni plate. Now, Chladni plate's basically a metal plate attached to the top of the speaker. There's sand on top of the plate, and you play different tones through the speaker. The plate vibrates, which forms different shapes depending on the frequency of the sound.
Well, we blew up a lot of speakers with the Chladni plate. So there was a lot of experimenting around the Chladni plate, primarily looking at how much volume we can put through there, how much sand to actually put on the plate, and the different shapes of plates and what different patterns would be created because of those shapes. But what we were really testing was what frequencies create the most interesting repeatable patterns, because that was a key point. So we ended up playing pretty much every audio frequency through the plate to see what different shapes it would form.
And for most frequencies, it doesn't really do much, but when it hits a frequency that resonates with the plate, it forms a really nice pure shape. So we found out what those tones were, and those were the tones we used to draw the plate in the video.
Oh, sorry, Rachel, I just saw your message. I'll post that. That link is on the PowerPoint slides already. Just click the top there and you'll see it. What they were describing in the video is that plate that they make, when they resonate just the right frequencies through it, you get a cool 2D pattern like the one shown in this picture here. For some reason, I can't see anybody anymore. My entire gallery is gone. Makes me quite sad. All right, but anyways, so we see these cool shapes and patterns, and they are resonant frequencies. So this is another way of saying the standing waves on this plate take a form where you get little troughs and the sand falls into the troughs on those standing waves. And that's just, it's a really cool kind of visualization of what a standing wave looks like in 2D. If we want to go to 3 dimensions, like a standing wave for an electron would be around a nucleus, we get something very special, especially to me as a chemist, and I think Rachel too. We get something called orbitals. Okay, and more on this next time, but here's just a little preview of what the 3-dimensional standing wave shapes kind of look like for these electrons in their orbits. Okay, so this is where we're heading. We'll definitely be watching and seeing this, how these come about and how that helps us understand elements. And then we're getting into periodic table stuff, so it's wonderful. All right, so that's that for now. I'd love to have any questions. I got a few minutes to stick around. Otherwise, don't forget your quiz by Sunday at midnight, and we'll see you all next week.